Hello, we're going to use the combustion TESTapp to do some energy analysis of a combustion reaction. In this case, we want to find heating values of methane as well as the adiabatic flame temperature. So let's go and start the TESTapp that we need. We go to the testicle tabs and we will start with the open, steady, specific combustion chamber. So we have a steady flow system, steady flow reactor in which fuel and oxidizer they enter, and this is called non-premixed combustion. And we'll pick up IG model. The PG model means CP will remain constant. IG model is a little more accurate, and we click the HTML5 button to launch the test. So here methane is a fuel, 1 kilomole of methane, and we want to find the heating value. So methane is reacting with air. Generally, heating value is found when methane is theoretical. The reaction is theoretical, so we pick theoretical combustion with air. So that's the reaction that we want. And so for this particular reaction, we want to find the heating value and the adiabatic flame temperature. Well, if any other reactions, the process for energy analysis will remain the same. So what is heating value? Heating value means the oxidizer and fuel come at 298 Kelvin. Products which are hot are cooled down to 298 Kelvin. So the amount of heat that you can extract as a result is called the heating value. And if the H2O happens to be in vapor form, which is most usually the case, in that case is called the lower heating value, because you need heat to vaporize water. And if water comes out as liquid, then it's called higher heating value. Let's go to the state panel and evaluate the states. Fuel mixture enter set. Notice that state 1 is automatically keyed to fuel. Temperature is 298, and the mass will be picked up from the reaction. That's why you see there is no, you cannot enter yourself. So we said 1 kilomole is flowing every second, so it's converted to mass. So about 16 kg of fuel is coming in. If you go to state 2, automatically it is oxidizer. Again, pressure is they come at the same pressure and same temperature and of 298 standard temperature. And here's the oxidizer properties. Notice that in addition to overall properties, partial properties of each component is shown here. State 3, we have products. Again, for finding the heating value, we'll cool down the products exactly to the temperature of the reactants, which is equals T1. So all the three states are now known. How do we figure out the heating value? Okay, so in this particular case, how much heat is being taken out to make the products cooler? So let's call it Q dot out. That must be equals the enthalpy, the flow energy that all flows in. With fuel, how much is flowing in? This much. With oxidizer, m dot 2 times enthalpy of oxidizer per unit mass. And how much is going out? m dot 3, which is the products, times H3. So there are only 3 states you can calculate here so that mistakes are avoided. So Q dot out is found here, so many kilowatt, right? Because so many kg per second is entering. So this is what? This will be the heating value per kilomole of fuel, because we have 1 kilomole is flowing in. But if you want to say, okay, this would be the lower heating value, of course, lower heating value on the mass basis would be what? Would be Q dot out divided by m dot 1, because then we have per kg of methane how much heat is released, and that's the lower heating value, which is about 49.98 million joule per kg of methane. That's just the correct value. You can go and check. Now let's say we want to find the higher heating value. Well, to determine the higher heating value, we first recognize that the products cannot be containing vapor of water. So we will get rid of water by clicking the remove button and add equal amount of liquid water. In other words, the water is in condensed form in the product. As a result, we can extract more heat from the system. So the higher heating value, notice, oh, by the way, because we changed the product's mixture, we got to recalculate the product states. So if I hit the calculate button, we'll notice that the enthalpy will change. It will become more negative. And then on the I/O panel, to find the higher heating value, Q dot out, the formula doesn't change. Exactly, this is the same formula for amount of heat that is coming out. And so everything is correct except lower heating value should be called higher heating value for the purpose of aesthetic. It's just a variable name. So let's call it HHV, higher heating value. And now if I do the calculate, look, higher heating value is calculated to be about 55.5 million joules. This is in kilojoules per kg. Sorry, this is in kilowatt. This will be 55.5 megawatt, which means, but because we have 1 kg flowing of the fuel, so if you divide by the mass flow rate, the heating value is really, the unit is million joules per kg or kilojoules per kg. So we got the heating value correct for methane for both lower heating value and higher heating value. We'll calculate the adiabatic flame temperature in a separate video.